Hello class, welcome to the Stat 215 Lecture 3 video. This video is going to focus on the basics of probability. This lecture is going to have three objectives. First, we are going to learn the vocabulary of probability. Second, we will understand the difference between empirical and theoretical probability. And third, we are going to introduce 4 rules of formal probability. Let's start by looking at Objective 1, to learn the vocabulary of probability. Our first vocabulary term is random phenomenon. It's a situation in which we don't know what outcome, a situation in which we know what outcome can possibly occur, but we don't know which particular outcome will occur. So, for example, when we roll a 6-sided die, we know that our options are 1 through 6, but we don't know before we roll which of those 6 sides are going to land face up. Same thing if you have a deck of cards and you're drawing a card at random. You know what the possibilities are, but you don't know what specific card you're going to select. A trial in each occasion upon which we observe a random phenomenon. So, for example, it's one occasion of rolling a die or one card being selected. That is a trial. The outcome is the value of the random phenomenon for a trial. So if you roll a 6-sided die, that situation of not knowing what you're going to get is a random phenomenon. The act of rolling once is a trial. Rolling and getting, say, a 5 face up, that's the outcome. So for some synonyms of outcome, you might hear as element, member, or sample point. A sample space is the collection of all possible outcomes, and it is denoted by the capital letter S. So for example, S equals 1, 2, 3, 4, 5, 6 when we're rolling a die. An event is a combination of possible outcomes from our sample space. And so we should note a single outcome can be your event of interest. So, meaning that if we're only rolling the dice once, then our trial is going to be a singular event. If we're going to do it multiple times, then it can get a little more complicated. So, let us suppose a fair die is tossed. Again, our sample space is going to be 1, 2, 3, 4, 5, 6. So if we consider the event of rolling an odd number, say call it A, then A equals 1, 3, or 5. If we consider the event of rolling a number greater than 4, let's call that B, then we'll say B equals 5 or 6. When we look at a trial, so say we flip 2 coins, and we'll assume that they're fair-sided coins, then our trial is, again, the flipping of 2 coins. Our sample space is going to be HH, meaning heads, heads, HT, heads, tails, TH, tails, heads, or tails, tails. Sometimes this is easier to see a sample space if we show it out visually. So, for our first toss of the coin, you can have either heads or tails. For our second coin toss, again, it's going to be heads or tails, but we are going to throw it for the second time, so our first coin flip has already been determined. Now we just have our second options. So again, we're either going to have a heads on the first toss and then heads or tails on the second toss, or we'll have a tails on the first toss and heads or tails on the second toss. So, one possible event of interest might be the event where we have exactly 1 tails. So that would be heads, tails, or tails, heads. So to go into sample space a little bit more, let's look at the sample space rule method. Sample spaces with a large or infinite number of outcomes are best described by a statement or rule method. For example, suppose the possible outcomes of an experiment are the set of cities in the world with a population over 1 million. So to show this sample space, we will let S equal X given X is a city with a population over 1 million. When you see this vertical bar in probability, that means given. Let's take a look at another situation. So let us have S be the set of all points, x, y, on the boundary or interior of a circle centered at the origin with a radius of 2. So in this case, our sample space is going to be S equals x comma y given x squared plus y squared is less than or equal to 4. Now that we've gotten a good idea of the sample space, let's get into some rules, starting with the complement. So the complement of event A with respect to sample space S is the subset of all elements of S that are not in A. When we denote the complement of A, we do it as A prime. So for example, if we have a fair die, our sample space is once again 1, 2, 3, 4, 5, 6. And if we let event A be the rolling of an odd number, then event A is 1, 3, and 5. The complement of event A is its opposite, meaning it's the probability, not the probability, haven't gotten there, the event that we roll an even number. So 2, 4, or 6. So complement means opposite. One nice thing about probability is a lot of times we can draw things out visually, particularly with Venn diagrams. So let's take a look at the Venn diagram of a complement. So we'll let set A be A, and we'll let its complement be denoted as A prime. So together, they make up our entire sample space S. So all of this is our sample space. We let A be this blue circle, and the opposite of it, everything else in the square, is A prime, or our complement. Now we've looked at the rule for the complement, let's take a look at the rule of intersection. So intersection of two events. The intersection of two events, A and B, are often denoted by A, and we have this opposite of the U, which I'll just refer to as intersection, B. And it is the event containing all the elements that are common to A and B. Let's take a look at an example. So for our fair die, once again, our sample space is 1, 2, 3, 4, 5, 6. So we're going to let A be the rolling of an odd number. We'll let B be rolling a number that's greater than 3. So our event A, rolling an odd number, will have the subset 1, 3, 5. Our event B, rolling a number greater than 3, will be 4, 5, and 6. We are asked to find the intersection, which is the event or events containing all the elements that are common. So if we take a look, for event A, our first item or outcome is 1. There is no 1 in B, so that's not going to be in the intersection. Next, they have 3. 3 is not in B, but then we have 5. 5 is also included in our event B. We also have event 4 and 6 in B, but those are not in A. So that leaves our intersection of A and B to be the event or outcome 5. Let's show this visually with a Venn diagram. So we have two sets, A and B. The event, A and B, again, their intersection. So we have our first circle A in green and our circle B in blue. The part where they overlap, purple, is that light blue, A and B. This is the intersection. Helpful hint, when you're reading word problems about probability, when you see the word "and," that means intersection. What is the probability of A and B? That means what is the probability of the intersection of A and B? Let's take a look now at disjoint events. Two events, A and B, are disjoint if the intersection of A and B equals our empty set. That is, if A and B have no elements in common. Another synonym for this is called mutually exclusive. So to make an example of this using our fair die, you can recall that our sample space is 1, 2, 3, 4, 5, 6. We let event A be the event of rolling an odd number. We let event B be the rolling of an even number. If we take a look, event A is equal to 1, 3, 5. B is 2, 4, and 6. None of the values in A are also in B. So that means their intersection is going to be the empty set. Let's take a look at this visually. So disjoint events, when we have two disjoint events, A and B, notice that there is no overlap. If you're selecting an event in this diagram, you can either be in A, B, or neither in A or B. But you cannot be both A and B. There is no overlap, there is no intersection. Let's take a look at kind of the opposite of disjoint events, and that is the union events. The union of two events, A and B, denoted as A, something that looks kind of like a U, again, U, union. B is the event containing all the elements that belong to A or B or both. For example, using our fair die, we have our sample space of 1, 2, 3, 4, 5, 6. We are going to let event A be the rolling of an odd number. We are going to let event B be the rolling of a number greater than 3. So, for our event A, rolling an odd number, that will give us a subset of 1, 3, 5. For B, rolling a number greater than 3, we'll have 4, 5, and 6. The union contains all elements of A or B or both. So that means we're going to have 1, 3, 4, 5, and 6. Remember, union and intersection are not the same thing. Union contains all elements from both sets. Intersection just contains elements that are common in both. We can take a note at this point that the union of A and A complement is the entire sample space. That's kind of a nice rule to know. Let's take a look at a Venn diagram. So we have two sets, A and B, and we want to know event A or B is their union. Notice before when I said we had and represented intersection in word problems, in a similar fashion, when you see the word or in word problems for probability, that implies the union. So, using the same diagram that we use for intersection, we have the part that's just A, the part that's just B, and our overlap of A and B, which is the intersection. Our union is all of A and all of B. Everything that's shaded is our union. This brings us to our second objective, understanding the difference between empirical and theoretical probability. So, let's start by defining probability. Empirical probability of event A. So we show this as P of A, or probability of A, equals the number of times A occurs over the number of trials, in the long run that is, aka it is the relative frequency probability. This is a formula that you're definitely going to want to memorize if you haven't already. Now, something that might be a little new to you is something called the law of large numbers. For many independent trials, the proportion of times event A occurs will converge to its probability of A. So let's consider the concept of flipping coins. Now, theoretically, you know that if we're trying to gauge the percent of times heads will be heads up, theoretically, that should be 50%. However, if you throw one flip of a coin, you may get heads or you'll get tails. The second flip, you may get heads and you may get tails. But the more flips you do, eventually, if you were to converge all of that probability together, your number of heads versus your total number of flips, that should converge to be 50%. You can see this visually in our chart here, where it slowly changes our probability, the number of trials that occurs. So even with just, say, 30 flips, we start getting pretty close to 50%. That is the law of large numbers. Now, another concept is something called equally likely outcomes. This occurs when we say roll a die, flip a coin, draw a card from a deck. It means that all events are equally likely to occur. So in our three examples, all sides of the dice are equally likely to be heads up. Same thing with heads and tails. You have a 50-50 chance of it being heads or tails. And pulling a card from a deck, you have a 1 in 52nd chance of any of those cards being selected. Next, we can be defining probability for our equally likely outcomes. So when all outcomes in our sample space are equally likely, then the probability of event A occurring is the number of outcomes in A over the number of possible outcomes in our sample space. Let's start taking a look at an example. So let's think about some U.S. currencies. So the Treasury currently issues 7 different denomination of notes. We have a $1 bill with our George Washington. 2, we have Thomas Jefferson. 5, we have Abraham Lincoln. 10, we have Alexander Hamilton. On the $20 bill, we have Andrew Jackson. On the $50 bill, we have Ulysses S. Grant. And then on the $100 bill, we have Benjamin Franklin. So if we're looking at our example, suppose you have one bill of each in your wallet, and you're going to select one bill at random. So selecting a bill is a trial, and again, the outcome is the denomination you select. Our sample space would be the $1, $2, $5, $10, $20, $50, and $100. Our event A, let us select a bill with a president on it. Well, if we scroll up, George Washington was a president, Thomas Jefferson was a president, Abraham Lincoln was, Alexander Hamilton was not a president, Andrew Jackson was a president, Ulysses S. Grant was a president, Benjamin Franklin was not a president. So our event A is going to be the $1, the $2, $5, $20, $50. So now we can use this to calculate our probability. So again, the probability of A is the number of outcomes in A, which in this case is 1, 2, 3, 4, 5, over the number of possible outcomes in our sample space, which is 1, 2, 3, 4, 5, 6, 7. So this gives us a probability of A to be 5/7. Hopefully, that's not too bad. Let's take a look at some more examples. So now we are going to let event B be selecting a bill without a building on it. Let's go back and look at our U.S. currency. So at first I was just paying attention to the presidents. Now we're going to have to pay attention to the backside. So we have for the $1 bill, we have the Great Seal of the U.S. 2 is the signing of the Declaration of Independence. 3 is our Lincoln Memorial. 4, or rather the $10 bill, has the U.S. Treasury Building. 5 is, oh wow, I keep saying the numbers, I should say the bills to keep it a little bit easier. The $20 bill has the White House, the $50 bill has the U.S. Capitol, and the $100 bill has Independence Hall. Let's go back and look at our example. So we want the probability, we want B to be an event without the building on it. So, Independence Hall is a building, Capitol Hill is a building, the White House is a building, the Treasury Building is a building, and the Lincoln Memorial is a building. So it looks like the only places that are not a building is the Great Seal of the U.S. and the signing of the Declaration of Independence. So that is going to give us our subset of the $1 and the $2 bill. Meaning our probability is going to be 2 out of the number of cases, which is 7. Not bad. Let's do D. We want to select a bill that can pay for your $12 lunch. Okay, so the way I'm interpreting that is if you go to the cashier and they say your lunch is $12, you want to hand them a single bill, not multiple. So I'm going to say it needs to be a bill that has to be greater than 12, which in this case would then be the $20, $50, and the $100 bill. Let's go back. So again, the outcomes in event D are the $20, the $50, and the $100. Therefore, our probability of event D is going to be 3 out of 7. Not too bad, right? Let's do one more. What is the probability of selecting a bill that won't pay for your lunch? Okay, so meaning we want the opposite of event D, or we want the complement. So the bills, let me try to make my bracket look a little bit better, that cannot pay for your $12 lunch is the $1, the $2, the $5, and the $10. This means the probability of our complement is going to be 4 out of 7. Another way to have gotten this would have been using the rule of the complement, which we haven't discussed formally, but I feel now is appropriate time to bring it up. We know the probability of something being in our sample space is going to be equivalent to 1, meaning the probability of our sample space is 7 out of 7. Make sense? There are 7 items in our sample space, and the probability of selecting one of those at all would be our 7 out of 7. Sorry, I misspoke. Obviously, selecting just one of those events is 1 out of 7, but if we take the probability of the union of all of those events, that would be 7 out of 7. So, if we subtract our 7 out of 7, the probability of the sample space, minus the probability of event D, that will give us our result. Or this highlights the rule of the complement. If we think back before, we learned that the union of A and its complement equals the sample space. Well, same thing here. The probability of D and the complement is going to equal the probability of our sample space. Meaning 4/7 plus the probability of our complement is going to equal 1. Just a little tidbit to know. Let's move on. Okay, so still continuing with our U.S. currency example. We are going to define, let A equal the set of bills with an odd number value. B is the set of bills without a building on the back. So, drawing this out visually, we know that the set of bills with an odd number value is 1 and 5. For B, the set of bills with a building on the back is 5, 10, 20, 50, 100. If we are drawing this out visually, we can notice that there is an overlap with our bill 5. It is both an odd number value and there's a building on the back. Notice that the $2 bill is outside of both our events A and B. So, if we are asked to find the intersection of event A and B, that is going to be the probability of just selecting the $5 bill, which is going to be 1 out of 7 because there is just the one event out of a total 7 events. Let's take this concept a little bit further. So counting sample points. So sometimes we are going to need to be able to determine the number of elements in S, our sample space, in a more complex scenario. This introduces us to the multiplication rule for counting. If one operation can be formed in n1 ways, a second operation can be formed in n2 ways. And ... a kth operation can be formed in nk ways, and k operations can be formed in n1, n2, all the way to nk ways. So let's take a look at an example of this multiplication rule. So suppose we have 4 exterior styles and 3 floor plans for building a house. We are curious to know how many different ways can a home buyer order a house. Now, one way to do this is to try to figure it out visually. So we've got our 4 styles and our 3 plans. So say our exterior styles are Tudor, rustic, colonial, and traditional. And then our floor plans are ranch, 2-story, and split level. So one way to do this would be to count. So we've got Tudor, ranch, Tudor 2-level, Tudor split level, so on and so forth, and we could count and say we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 different ways to buy a house. The alternative way, and a way that would be faster than drawing out this diagram, is to multiply. We have 4 exterior styles times 3 floor plans equals 12 ways to order a home. That's a lot faster. Let's take a look at another example. Sam is going to assemble a computer by himself. He has the choice of chips from 2 brands, a hard drive from 4, memory from 3, an accessory bundle from 5 local stores. How many different ways can Sam order the parts? Okay, so we've got 2 brands, a hard drive from 4, memory from 3, and an accessory bundle from 5 stores. If we multiply our options together, we see that there is 120 ways for Sam to order the parts. Hopefully, this was not too bad. Let's move on to a similar topic called permutations. A permutation is an arrangement of all or part of a set of objects. So let's consider we have 5 Olympics. We consider the fact that we have 5 Olympic skaters. How many ways is there to assign a medal? Well, first off, when you're running the race, how many people at the start of the race have the opportunity to win the gold medal? The answer is 5. Once that first person crosses the, say, finish line, how many people now have the opportunity to win the silver medal? Well, can't be 5 because we already have 1 person who's crossed the finish line. So that leaves 4 individuals that are still left in order to try to get the silver. After that person wins the silver medal, we have 1 person in gold, 1 person in silver. How many people do we have remaining to try to win the bronze? We have 3. At this point, we can now calculate how many ways to assign the medals by our multiplication rule. So 5 times 4 times 3, which will equal 60 ways. So with 5 Olympic skaters, there are 60 ways to assign the medals. Taking this a step further, let's talk about the concept of factorials. So let n be a whole number, 0, 1, 2, all the way to, infinity if it was possible. So we will define n factorial as n exclamation point, again you'll hear me refer to this as n factorial, as n multiplied by the quantity of n minus 1 factorial, with 0 factorial equal to 1. So in that case, we know 0 factorial would equal 1, 1 factorial is going to equal 1, 2 factorial will be 2 times 1, which equals 2, 3 factorial will be 3 times 2 times 1, which in this case would equal 6. Basically, factorials involve a little bit of counting backwards. So, using our Olympics example, we have 5 factorial over 2 factorial. Expanding out our factorials, in our numerator we have 5 times 4 times 3 times 2 times 1 over 2 times 1. By crossing out, whoopsie-daisies, we are still left with what we had previously, the 5 times 4 times 3, which equals 60 ways. At this point now we can be introduced to the formula for permutations. So the number of permutations of n distinct objects taken r at a time is n permutate r, or NPR, kind of like the radio show, equals n factorial over the quantity of n minus r, n quantity factorial. Using this in our Olympic example, that's going to be 5 permutate 3, which is going to be equal to 5 factorial over the quantity of 5 minus 3 factorial, which again would still equal 60 ways. Let's expand this example. So, how many ways can you select a president and vice president from 4 candidates? So, let us arbitrarily name our candidates as A, B, C, D, just to make things easier. So, for president and vice president, there are 2 positions. So, using our formula of n factorial over the quantity of n minus r factorial, we can do 4 permutate 2, which would equal 4 factorial over the quantity of 4 minus 2 and quantity factorial. Expanding out, that will give us 4 times 3 times 2 times 1 in our numerator and 2 times 1 in our denominator. To make things easy, let's cross out, and that gives us 4 times 3, which would equal 12 ways. We could also do this in a chart, as seen here. And we could simply count the number of ways, and clearly if we count, we'll have 12 ways. But, as always, I like to do things a little bit shorter and a little more mathematically sound. Now that we've talked about permutations, let's move on and talk about combinations. It's important you keep permutations and combinations straight because these concepts are definitely similar. So let's consider our president and vice president example. In that case, it mattered. Being vice president and president are 2 distinct positions. Well, for now we consider, what if order doesn't matter? That is, what if it didn't matter who was president and who was vice president? All we wanted were a distinct number of pairs. In other words, we wanted to know the number of unique combinations. So, for our combination examples, how many ways can you select 2 candidates from 4 candidates? Meaning, instead of having our 12 permutations, instead, we could just have 6 combinations. So in this case, for permutations, candidate AB and BA were distinct. AB meant the A was the president, B was the vice president. BA, B was the president, A was the vice president. If order doesn't matter and we're just selecting 2 people for some leadership position, in that case, AB and BA are considered to be the exact same. So, let's now formally define combinations. So it is the number of combinations of n distinct objects taken r at a time. So for our formula, we have n and r over each other in parentheses. We'll call this n choose r. And the formula for this is going to be n factorial in our numerator over r factorial multiplied by the quantity of n minus r factorial. So in our case, using our president's example, we would have 4 factorial over 2 factorial multiplied by the quantity of 4 minus 2 factorial. Expanding this out, that means in our numerator, we would have 4 times 3 times 2 times 1 over 2 times 1 multiplied by the quantity of 2 times 1. I still like to cross things out and simplify where I can. So I know that we can simplify 4 over 2 to be 1 in the denominator, 2 in the numerator, and that gives us 2 times 3, which equals 6. You could also do this the long way. At this point, we can take a note that for our permutations, it was 4 permutate 2. And we were given 4 factorial over the quantity of 4 minus 2 factorial, which equaled 12. For the combinations, what it really was 4 permutate 2 over 2 factorial to give us our combination of 6. Let's take a look at another combinations example. In a sequence of 5 coin flips, how many ways are there to get exactly 3 heads? So, we want 5, choose 3. Using our formula, that's going to be 5 factorial over 3 factorial multiplied by the quantity of 5 minus 3 and quantity factorial. So to simplify this, that's going to be 5 factorial over 3 factorial multiplied by 2 factorial. At this point we can simplify or expand. So in our numerator, 5 times 4 times 3 times 2 times 1. The denominator, 3 times 2 times 1, and 2 times 1. As always, I do like to cross things out just to make it simpler. So that's going to leave 5 times 4 over 2 times 1, which is going to equal 20 over 2, or 10. So, in answer to our question, how many ways are there to get exactly 3 heads when we have 5 coin flips? There are 10 ways. Very good. This brings us to the end of Objective 2. Let's move on to Objective 3. So, for our third objective, we are going to be introduced to the 4 rules of formal probability. Let's take a look at Rule 1. So, for any event A, 0 less than or equal to the probability A is less than or equal to 1. Translation, all probabilities must be between 0 and 1. Meaning, you can't have a negative 25% chance of winning and you can't have a 120% chance. That makes no sense. Also note, probabilities are written as decimals. So a 45% chance is going to be written as the probability of, say, event A equals 0.45. Next rule, Rule 2, that I brought up already, is the probability of our sample size equals 1, meaning the set of all possible outcomes has the probability of 1. Meaning, if we are flipping a coin, there is a 100% chance you will get a head or a tail. Rule 3, something I've also introduced you to already, is the complement rule, which states that the probability of the complement of A equals 1 minus the probability of event A. So, for example, if we are rolling a fair die, we will let A be 6. So therefore, the probability of rolling a 6 is going to be 1 out of 6. Therefore, the complement, or the probability of A prime, equals the probability that we don't roll a 6. Using our rule, that's going to be 1 minus 1/6, which would equal 5/6. Finally, this brings us to Rule 4. If events A and B are disjoint, then the probability of A or B, also known as the union of A and B, equals the probability of A plus the probability of B. Again, this is the addition rule for disjoint events. For example, let's roll a fair die. We can recall that our sample size is 1, 2, 3, 4, 5, 6. The probability of our sample size equals 1. We are going to let event A be the event of rolling a 2, and we are going to let event B be that we rolled a 5. So, given that the probability of A and B are disjoint events, they cannot happen at the same time, the probability of A or B is going to equal the probability of A plus the probability of B. The probability of A is going to be 1/6. the probability of B is also 1/6. Take the sum of 1/6 plus 1/6, and that'll give us 1/3. I also want to give you a corollary to our Rule 4. If A1, A2, all the way to AN are mutually exclusive, meaning they're disjoint, then the probability of the union of event A1, A2, all the way to AN equals the probability of A1 plus the probability of A2 plus ... the probability of AN. Let's take a look at let's look a little deeper into our formal probability rules. If A1, A2, all the way to AN is a partition of our sample space, then the probability of the union of A1, A2, all the way to AN equals the probability of A1 plus the probability of A2 plus ... all the way to the probability of AN equals the probability of our sample size, which will equal 1. To properly define this, a partition is mutually exclusive events that together make up our whole sample space. Just to show what this might look like visually, if I draw a box and I partition it into 4 parts and say this is A1, A2, A3, A4, together the whole sample space is S, and we know that the probability of S equals 1. However, we can also see that if we add up our 4 partitions, that will also be the entire sample space, and therefore it will also equal 1. Another example of this would be, let our sample size be equivalent to the freshmen, sophomore, juniors, and seniors of the undergraduate class. Is this a possible probability distribution for freshmen, sophomore, junior, seniors? 0.25, 0.23, 0.22, and 0.20. Well, let's think about this. You are either a freshman, sophomore, junior, or senior, correct? So, if we add them all together, they should equal 1. If they don't, we have a problem. So let's add them up. So 0.25 plus 0.23 plus 0.22 plus 0.20. Well, unless my math is wrong, I got 0.90, which does not equal 1. So, is this a possible probability distribution? The answer is no. Not when we're talking strictly about the undergraduate class. Now, at this point, since we're still talking about the addition rule, I'd like to do a little bit of a subset of it. Let's call this Rule 4A. If A and B are 2 events, then the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Remember, when we see that U symbol, that's the union. When we see the reverse, that is the intersection. To show what this looks like visually, we are saying that the probability of the union equals the probability of event A plus the probability of event B. But if you'll notice, we have counted this center section twice. Well, that's not okay. When we count things, we only want to count it once. So, because we counted the center section, the intersection, twice, we need to subtract it out once. And the reason we call this 4A is because if there's no overlap in the probability of A and B, then it's sufficient to just add them. Because if we're trying to find our probability of the union of A and B, and this is our A and B, then it will be sufficient to add our two events without our intersection because there is no intersection. I hope that made sense. Again, when we have two disjoint events or mutually exclusive, there's no overlap, there's no intersection. So that means the intersection is equal to 0, which is why previously our old rule was just the probability of A plus the probability of B. At this point, let's go back to our US currency example and do some addition. So, let event A be the set of bills with an odd number value, and we are going to let event B be the set of bills with a building on the back. So, if we wanted to find the union of A and B, we would not just say we've got the probability of event A plus the probability of event B. A, we can see, is 2/7 and B is 1, 2, 3, 4, 5/7. That equals 1. That is a full partition. That's our whole sample size. We can move on. Well, showing it now visually, we've got an issue. One, it's definitely not the full sample size because we left out 2. Also, we counted $5 twice. So this should be a good indication that we need to use Rule 4A, which is the probability of A, which is the 2/7, plus the probability of B, our 5/7, but because we counted 5 once, we need to subtract it out. So minus 1/7, which will give us 6/7. Hopefully this is not too bad. If not, you may want to take some time and do some extra practice. Let's do another example. The probability that an American company will build a new factory in Shanghai is 0.7. The probability it will build a new factory in Beijing is 0.4. And the probability it will build a new factory in Shanghai, Beijing, or both is 0.8. What is the probability that the company will build a factory in both cities? All right, so when I'm doing these types of problems, I like to write out everything first. So I'm going to let S, in this case, be Shanghai, just to keep things a little simpler. So we know that the probability that the factory is built in Shanghai is 0.7. The probability of it being built in Beijing is 0.4. And we know that the probability that it will be built in Shanghai, Beijing, or both is 0.8. Now, because that's all options, I'm going to go ahead using my context clues and realize they're talking about the union of the event, which is 0.8. We want to know the probability that the company will build a new factory in both cities, meaning what is the probability that we build in Shanghai and Beijing? We are asked to find our intersection. So in order to do this, we need to use our addition rule. So we know that the probability of the union of Shanghai and Beijing equals the probability of Shanghai plus the probability of Beijing minus their intersection. At this point, we can do the old-fashioned plug and chug. 0.8 equals 0.7 plus 0.4 minus our probability of both cities. So if we do the math correctly, we should get that the probability that the company will build a factory in both cities to be 0.3 or 30%. Again, if this went a little fast for you, make sure you go back and practice on your own. Let's take a look at another example. What is the probability that the company will build a factory in neither city? So, we know that the probability that they build in just Shanghai, just Beijing, or both is the union. We want the opposite of the union. So we want the probability that it's not in Shanghai. Oops, let me erase that. It's not both, and it is not in Beijing. And as we said, this is the opposite of the union of our event. So we are going to use the complement rule. 1 minus the probability of it being in just Shanghai, just Beijing, or both. So that's going to be 1 minus 0.8, which equals 0.2. So there is a 20% chance that the company will build a factory in neither city. Let's do another example. The general addition rule. In 2016, the Pew Research found that 79% of online adults were Facebook users, 24% used Twitter, and 22% used both. Draw a Venn diagram to display these results. Okay, so just going to start off by drawing my box. Now, because I see that we had 22% use both, that means I'm going to draw 2 circles that overlap. So I'm going to let my first circle be Facebook users and my second one be Twitter users. Now, we were conveniently given that 22% use both. That's going to be our intersection, or this section right here in the middle. So 22% use both. Now, at this point, you might be tempted to say, all right, we are going to put 79 here and 0.24 here. There, we're done. Let's move on. Hold up. This is not right. Remember, the 79% of online adults that were Facebook users, that includes the 22% that used Facebook and Twitter. We're counting it twice, and we did the same thing with Twitter. So we need to subtract. That means that our 79% minus our 22% gives us 57% or 0.57. These are the people that are Facebook only users. We'll do the same thing with Twitter. 0.24 minus 0.22, that's our overlap. Subtract, that gives us 2% or 0.02. These are the people who are only Twitter. Okay, very good. Now, just for the fun of it, we've got our Facebook users, our Twitter users, the people who use both. What about the people who use neither? Let's figure them out. So we should know, using our rule, that if we add up 0.57, 0.22, and 0.02, that will give us our union. And that equals 0.81. So that is the number, or rather the percent, of people who use Facebook, Twitter, and both. Now, to find the people who are neither users, we should subtract 1 using our complement rule. So 1 minus 0.81 equals 0.19. So 19% of people use neither Facebook nor Twitter. Okay, we're really rolling now. Let's do one more example. Let F equal the respondents that use Facebook. Let T equal the respondents that use Twitter. We're going to use the diagram that we've already built to answer these questions. So, who uses Facebook and Twitter? Well, we are asked Facebook and Twitter. When we see the word and, that means intersection. So that's going to be 0.22, intersection. Next, we're asked, uses Facebook, but not Twitter. So we want the probability of uses Facebook, but not Twitter. So we want the intersection of Facebook users and not Twitter users. That's going to be 0.57. Let's move on to the next one. We want the neither Facebook nor Twitter. So, if we need to do this visually, uses neither Facebook, meaning not Facebook, and also doesn't use Twitter. Well, that's going to leave us with that 19% that are neither Facebook nor Twitter users. Let's take a look at the last one. Uses Facebook or Twitter, but not both. So in this case, there's two ways to calculate this. One, we could find the probability of people who use Facebook and not Twitter with the union of people who don't use Facebook but do use Twitter, and that would give us 0.57 plus 0.19. Again, because we want the people who use Facebook but not Twitter, and the people who use Twitter but not Facebook. We could also use the complement rule, where we know that the union of Facebook, Twitter, and both is 0.57 plus 0.22 plus 0.02, and then we could take out the 0.22, but that seems like an extra step. Oops, typo. That should not be 0.19. That should be 0.2. But when we're using this visual representation, I think it's easier to see when we're saying Facebook or Twitter, but not both. It's easier to see that we would add 0.57 and 0.02 instead of using some of the complement rule. Okay, so that brings us to the end. Let's just summarize what we've learned so far. So, this lecture we have learned how to find probabilities of events. We know that events are made up of outcomes, and outcomes come from trials of a random phenomenon. We know that probabilities are always between 0 and 1. Probabilities for all outcomes in a sample space are going to add up to 1, and if the event or outcome isn't possible, that's going to be equal to 0. We learned the complement rule that says the probability of the complement of A equals 1 minus the probability of A. We learned that you can add the probability of disjoint events A and B to find the probability of A or B occurring. And finally, we learned to use the general addition rule to find OR probabilities when events are not disjoint. That's pretty good for today. So we're going to stop here. Have a good night, and as always, if you have questions, please feel free to email me.